According to the Virginia Building Code, specifically Section 305.1.1, a permit is required for any electrical work that alters or modifies the voltage or amperage of an existing electrical system. It's important to note that the Virginia Building Code does not explicitly state that electrical service upgrades exceeding 800 amps require professional engineer's seal. Similarly, the National Electrical Code, which is adopted by the Virginia Building Code, does not mandate a professional engineer's seal for electrical service upgrades surpassing 800 amps. However, the National Electrical Code emphasizes that all electrical work must be performed by a licensed electrician and that the installation must strictly adhere to both the National Electrical Code and all applicable local building codes. It is possible that the architect is misinterpreting the National Electrical Code or Virginia Building Code requirements. To clarify this discrepancy, you should reach out to the architect and request that they provide specific code references or regulations that substantiate the demand for a professional engineer's seal. Given the absence of specific code requirements for a professional engineer's seal on electrical service upgrades over 800 amps in Virginia, it is recommended that you continue collaborating with your licensed electrician to finalize the design and installation of the electrical service. If the architect remains unconvinced, you might consider seeking clarification from a local electrical inspector or a code enforcement official. The relevant code references include Virginia Building Code Section 305.1.1 and National Electrical Code Article 110.2 and Article 305. Let's delve deeper into the National Electrical Code, often abbreviated as the NEC. The National Electrical Code serves as the benchmark for safe electrical design, installation, and inspection to protect people and property from electrical hazards. It's important to remember that the National Electrical Code is not law unless it is formally adopted by a state or local jurisdiction. Article 110 within the National Electrical Code addresses the general requirements for electrical installations. This article covers various aspects, including the examination, installation, and suitability of equipment. Section 110.2 specifically focuses on the integrity of electrical equipment and systems. It states that electrical equipment must be installed in a neat and workmanlike manner. This implies that installations should be performed in a way that is both aesthetically pleasing and functionally sound. Workmanlike installations minimize the risk of future problems and ensure the long-term reliability of the electrical system. Article 305 of the National Electrical Code provides temporary electrical power requirements for construction, demolition, modification, repair, and similar activities. This article is crucial for ensuring safety on job sites where temporary electrical systems are used. These temporary systems often have different requirements than permanent installations. Article 305 outlines the grounding and bonding requirements for temporary electrical systems, as well as the types of wiring methods and overcurrent protection that are permitted. The goal is to minimize the risk of electrical shock and fire hazards during construction or other temporary work. Now let's shift our focus back to the voltage and amperage considerations of an electrical system. The 120/208 volts 3-phase 4-wire electrical service you mentioned is a common configuration used in commercial and industrial buildings. The 120 volts represents the voltage between a phase and a neutral conductor, while 208 volts is the voltage between two phases. The 3-phase configuration provides a more efficient distribution of power compared to a single-phase system. The 4 wires consist of 3-phase conductors and 1 neutral conductor. The neutral conductor provides a return path for unbalanced loads. An 800 amp service is a substantial electrical capacity capable of supplying a significant amount of power to a building. The specific power requirements of a building depend on its size, occupancy, and the types of equipment that are used. When designing an electrical service, it is crucial to accurately calculate the load demand to ensure that the service is adequately sized. Oversizing the service can lead to unnecessary costs, while undersizing it can result in overloading and potential hazards. The National Electrical Code provides detailed guidance on load calculations in Article 220. This article outlines the various factors that must be considered when determining the load demand of a building, including lighting, receptacles, HVAC equipment, and motors. It's also important to consider any future expansion or changes in occupancy that may increase the load demand. In addition to load calculations, it is essential to select appropriate conductors and overcurrent protection devices for the electrical service. The conductors must be sized to carry the calculated load current without overheating. The National Electrical Code provides tables in Article 310 that specify the allowable ampacities of different types of conductors based on their size, insulation, and installation conditions. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the conductors from overload and short-circuit conditions. These devices must be selected with an interrupting rating sufficient to handle the available fault current at the service entrance. The available fault current is the maximum current that could flow during a short circuit. It is determined by the utility's power system and the impedance of the service conductors. In Virginia, electrical work is regulated by the Department of Professional and Occupational Regulation, often abbreviated as the DPOR. The DPOR issues licenses to qualified electricians and contractors, ensuring that they have the necessary training and experience to perform electrical work safely and competently. It is illegal to perform electrical work in Virginia without a valid license, unless you are working under the direct supervision of a licensed electrician. The DPOR also investigates complaints against licensed electricians and contractors and can take disciplinary action, such as suspending or revoking their licenses for violations of the Virginia Uniform Statewide Building Code. In summary, when designing and installing an electrical service, it is imperative to comply with all applicable codes and regulations, including the Virginia Building Code, the National Electrical Code, and the regulations of the Department of Professional and Occupational Regulation. This includes obtaining the necessary permits, using qualified personnel, and performing thorough inspections to ensure the safety and reliability of the electrical system. Now, let's talk about some additional aspects to consider when dealing with electrical service upgrades and potential requirements for professional engineer involvement. Firstly, local amendments to the Virginia Building Code might exist. While the statewide Virginia Building Code and the National Electrical Code may not explicitly mandate a professional engineer's seal for service upgrades exceeding 800 amps, individual counties or municipalities within Virginia could have local amendments that impose stricter requirements. It's crucial to investigate whether any such local amendments apply in your specific jurisdiction. This might involve contacting the local building department or reviewing the local ordinances. Secondly, project complexity can be a factor. Even if not strictly required by code, the complexity of a specific electrical service upgrade project might warrant the involvement of a professional engineer. Factors that could increase complexity include non-standard voltage configurations, intricate control systems, integration with existing building management systems, or challenging site conditions. In such cases, the architect or building owner might reasonably request a professional engineer's seal to ensure that the design meets all safety and performance requirements. Thirdly, insurance requirements might come into play. The building owner's insurance company might have specific requirements regarding the design and installation of electrical systems. These requirements could include the involvement of a professional engineer for certain types of projects, regardless of what the building code specifies. It's advisable to check with the building owner or their insurance provider to determine if any such requirements exist. Fourthly, documentation and record keeping are essential. Maintaining thorough documentation of the electrical service upgrade project is crucial. This documentation should include detailed drawings, load calculations, equipment specifications, inspection reports, and any other relevant information. This documentation can be valuable for future maintenance, troubleshooting, or modifications to the electrical system. Furthermore, it can serve as evidence of compliance with applicable codes and regulations. Fifthly, communication is key. Open and clear communication with all stakeholders is essential throughout the electrical service upgrade project. This includes the architect, the building owner, the electrical contractor, the local building inspector, and any other parties involved. Addressing concerns and resolving conflicts proactively can help to ensure a smooth and successful project. Sixthly, consider a peer review. If there is disagreement about the need for a professional engineer's seal, consider having the electrical design reviewed by an independent, qualified electrical engineer. This peer review can provide an objective assessment of the design and help to determine whether it meets all applicable requirements. Seventhly, value engineering could be an option. If the cost of obtaining a professional engineer's seal is a concern, explore value engineering options. Value engineering involves identifying alternative design solutions that can reduce costs without compromising safety or performance. This might involve using different types of equipment, optimizing the layout of the electrical system, or simplifying the control system. Eighthly, be aware of future code changes. Building codes are periodically updated to reflect new technologies and best practices. It's important to stay informed about upcoming code changes that could affect electrical service upgrades. This might involve attending industry conferences, subscribing to relevant publications, or consulting with code experts. Ninthly, consider energy efficiency. When upgrading an electrical service, it's a good opportunity to consider energy efficiency measures. This might involve using energy-efficient lighting, installing variable frequency drives on motors, or implementing a building energy management system. These measures can reduce energy consumption and lower operating costs. Tenthly, prioritize safety. Above all, safety should be the top priority in any electrical service upgrade project. This includes following all applicable safety codes and regulations, using qualified personnel, and implementing appropriate safety procedures. Electrical work can be dangerous, and it's essential to take all necessary precautions to prevent accidents and injuries. In addition to the above, let's also consider aspects of electrical coordination and selective coordination, which are critical for ensuring the reliability and safety of an electrical system. Electrical coordination refers to the process of selecting and arranging overcurrent protection devices, such as circuit breakers and fuses, in a manner that minimizes the extent of an outage in the event of a fault. The goal is to isolate the fault to the smallest possible area, allowing the rest of the system to continue operating. Selective coordination is a specific type of electrical coordination in which overcurrent protection devices are designed to trip in a specific sequence, starting with the device closest to the fault and progressing upstream until the fault is cleared. This ensures that only the necessary devices trip, preventing unnecessary outages. Article 240.12 of the National Electrical Code addresses selective coordination requirements for overcurrent protective devices in emergency systems, legally required standby systems, and critical operations power systems. These systems are essential for maintaining critical functions in buildings such as hospitals, data centers, and emergency response facilities. The National Electrical Code requires that overcurrent protection devices in these systems be selectively coordinated to ensure that a fault in one part of the system does not cause a complete shutdown. Achieving selective coordination requires careful consideration of the time current characteristics of overcurrent protection devices. Time current curves illustrate the relationship between the amount of current flowing through a device and the time it takes for the device to trip. By comparing the time current curves of different devices, engineers can determine whether they will selectively coordinate. Several methods can be used to achieve selective coordination, including using fuses with different time delay characteristics, using circuit breakers with adjustable trip settings, and using zone-selective interlock systems. Zone-selective interlock systems use communication between overcurrent protection devices to ensure that only the device closest to the fault trips. Let's also discuss arc flash hazard analysis. An arc flash is a dangerous electrical explosion that can occur when a short circuit creates an arc of electrical energy. Arc flashes can cause severe burns, injuries, and even death. To mitigate the risks associated with arc flashes, it is essential to conduct an arc flash hazard analysis. An arc flash hazard analysis involves calculating the potential arc flash incident energy at various points in the electrical system. The incident energy is the amount of heat energy that a worker could be exposed to during an arc flash. The analysis also determines the arc flash boundary, which is the distance from the arc flash source at which a worker would be exposed to a hazardous level of incident energy. Based on the results of the arc flash hazard analysis, appropriate personal protective equipment, often abbreviated as PPE, can be selected. Personal protective equipment includes flame-resistant clothing, gloves, face shields, and other protective gear. The National Electrical Code requires that electrical equipment be labeled with information about the arc flash hazard, including the incident energy, the arc flash boundary, and the required personal protective equipment. Workers who are likely to be exposed to arc flash hazards must be trained on the hazards of arc flashes, the use of personal protective equipment, and safe work practices. In addition to personal protective equipment and training, engineering controls can be used to reduce the risk of arc flashes. Engineering controls include using current-limiting fuses or circuit breakers, using remote racking devices, and increasing the working distance from energized equipment. Now let's consider the topic of grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the fault. Bonding connects all non-current carrying metal parts of an electrical system together, creating a low impedance path for fault current. The National Electrical Code provides detailed requirements for grounding and bonding in Article 250. This article covers various aspects, including the types of grounding systems that are permitted, the size of grounding conductors, and the methods for connecting grounding conductors to equipment. A properly grounded and bonded electrical system minimizes the risk of electrical shock and fire hazards. It also helps to reduce electromagnetic interference and improve the performance of sensitive electronic equipment. Let's also discuss surge protection. Electrical surges are transient overvoltage events that can damage or destroy electronic equipment. Surges can be caused by lightning strikes, utility switching, or internal equipment malfunctions. To protect electronic equipment from surges, it is essential to install surge protective devices, often abbreviated as SPD. Surge protective devices divert surge current away from sensitive equipment, preventing damage. The National Electrical Code requires surge protection for certain types of electrical systems, including emergency systems, legally required standby systems, and critical operations power systems. Surge protective devices are rated based on their ability to withstand surge current. It is important to select surge protective devices with a sufficient surge current rating to protect the equipment being served. Surge protective devices should be installed at the service entrance and at branch circuits feeding sensitive electronic equipment. They should also be installed in accordance with the manufacturer's instructions. In addition to surge protection, it is important to implement power quality monitoring. Power quality refers to the characteristics of the electrical power supply, including voltage, frequency, and harmonic content. Poor power quality can cause equipment malfunctions, data errors, and reduced equipment lifespan. Power quality monitoring involves measuring and analyzing the characteristics of the electrical power supply to identify potential problems. Power quality monitors can detect voltage sags, voltage swells, harmonic distortion, and other power quality disturbances. Once power quality problems have been identified, corrective actions can be taken to improve the power quality. These actions might include installing harmonic filters, improving grounding and bonding, or upgrading the electrical system. Let's discuss about commissioning. Commissioning is the process of verifying that an electrical system is designed, installed, and operating according to the owner's requirements and the design documents. Commissioning typically involves a series of tests and inspections to ensure that all components of the electrical system are functioning properly. Commissioning can identify potential problems before they cause equipment failures or safety hazards. The commissioning process should begin during the design phase and continue through the installation and startup phases. A commissioning plan should be developed that outlines the scope of the commissioning activities, the roles and responsibilities of the commissioning team, and the schedule for commissioning. The commissioning team should include representatives from the owner, the designer, the contractor, and the equipment manufacturers. The commissioning process should include functional testing of all equipment and systems, including switchgear, generators, uninterruptible power supplies, often abbreviated as UPS, and lighting controls. The results of the commissioning tests should be documented in a commissioning report. A commissioning report should include recommendations for corrective actions to address any problems that are identified. Now let's discuss about maintenance. Regular maintenance is essential for ensuring the long-term reliability and safety of an electrical system. Maintenance activities should include periodic inspections, testing, and cleaning of electrical equipment. Maintenance should be performed by qualified personnel in accordance with the manufacturer's recommendations. A maintenance plan should be developed that outlines the scope of the maintenance activities, the frequency of maintenance, and the procedures for performing maintenance. The maintenance plan should also include a schedule for replacing aging equipment. Maintenance records should be maintained to track the maintenance activities that have been performed and the results of the maintenance. These records can be used to identify potential problems and to plan future maintenance activities. Common maintenance activities for electrical systems include inspecting and testing circuit breakers, inspecting and tightening connections, cleaning electrical equipment, lubricating moving parts, and testing grounding systems.